Hello and welcome. Today we're talking about logarithms. The expectation here is that you have a working knowledge of exponent and exponent laws. So this should be you. By the end you'll have you'll be able to derive the log laws. You'll have like a good basis to solve different logarithm problems. So to start, let's just recall what a power is. In a power, you have three values. You got your base, you got your exponent, which is your entire power, and another value that I want to call our number value. It's what the left part of the equation is equal to. So just to label it, we got our base, we got our exponent. This entire thing is called a power. And this is our number value. So, for example, you got your 10 squared equal to 10 times 10 equal to 100. You got your 5 cubed equal to 125. Okay. In a logarithm, you got those same three values. You got your base, you got your exponent, you got your number value, but they're going to be arranged differently. We're solving for something else. Verbally, how you read out a logarithm is log base a of b equals the exponent. So, for example, if we're going to abide by these two here, start with the 10 squared. We got log base 10 of 100 equals 2, and log base 5 of 125 equals 3. Next. So the ordering is different, and what we're solving for is different. Let's just label, just to make things more together, exponent. Conveniently, logarithms follow a log type. Logarithms follow a log type shape. As you can see, this little lovely swirl is what the logarithm follows. Got a to the x equals b. Right, so if you're familiar with the power, you'll be able to write out the logarithm by just remembering that log shape. That curly a to the power of x equals b shape. This relates the definition of a log, which is expressed here, right? That the log base a of b is x. It's the exponent that when a is raised to it gives b. But let's write this out a little bit differently. And let's make this a little bit prettier and less messy, because it's so messy. A raised to log base a of b equals b. Because once again, let's not forget that this value, log base a of b, is just our x, just our exponent, right? It's maybe a more messy way to write it, but it's a more descriptive way to write it. It's just the number when a is raised to it yields b. Okay. So just to clarify the distinction, let's just clarify what we're looking for, right? Because it's a math problem, solving for a quantity. So what quantity do we care about in each scenario? Scenario number 1, we care about what's left by itself. In this case, we care about the number value. When taking the power, we just want to find this b. Here, we're taking the inverse of an exponent, so we're finding the base. And then, with this new addition, we're solving for the exponent. Cool. This connection between logs and powers means you can translate power laws into log laws. These are close cousins, so they work together to give us new math to encounter. Power and logs. So, first power law we are gonna zero in on is the product of powers. Let's first when we are exploring this, let's take the log of both sides. So by doing this, we're just extracting the exponent. That when a is raised to gives us a to the x times a to the y. So this is a raised to something equals this. Equal to, because they're both the same overall value, right? Just to take that, a to x plus y. Well, we discussed our definition. This entire thing, just to reiterate, is the number that when a is raised to it gives us this thing. Oh, but this thing, the dark blue, we know that a raised to x plus y is equal to the blue thing. So, we can simplify that a bit. Left side stayed the same, right? We didn't do anything with that yet. Equals x plus y. Interesting. So this is saying pretty much from the exponent side what the top is saying. The exponent, the overall exponent that a is raised to when you multiply these together, or when you just have a raised to x plus y, is the same. Maybe written out a little bit nicer. We're gonna express these two in terms of their log forms, right? Because pretty much, and you're gonna see in a minute, I'm just a slow writer, log base a of a to the x, right? This is just x, because a raised to x is a to the x. And this is just y for the same reason. These two sides are equal. Still, because it's this step and this step. It's just a rephrasing. So this pretty much gives us our log law. But let's make it look more general, because this whole a to the x and a to the y is not how we're gonna see it when we're solving problems. So let's make ax equal b, because we've been doing that the whole time. And we'll make ay equal to c. So it's still general, because like b and c, they could be like whatever. So log base a of bc is equal to log base a of b plus a log base a of c. Pretty much, you adding the exponents, you add the exponents like after, or you're adding the exponents within here, because multiplication in the exponent or power world is addition. Multiplication is addition in the power world. So that's why this is reflected here. Let's lower this down and make this look pretty. So we'll make this yellow. Pretty enough, okay. Our next thing is quotient of powers. Very similar. Pretty much you're dividing, subtracting instead of adding. It's the same idea. In the interest of time, we're just gonna like work things out verbally. Let me know in the comments if you want me to like put a more detailed derivation of it. We're gonna keep these guys. Let ax equal b and ay equal c. So keep that in the back of your minds. Just so we can make it look general, because why not? Log of c over b. Division in the world of exponents is subtraction. So we are dividing number values, so we are subtracting the exponent values. Log base a of c minus log base a of b. Because which exponent are we subtracting? What's being subtracted is what's being divided. So a to the x is what's fueling our subtraction. So we're subtracting our x. This is our value x. And that's all to it. That's all it. That's all it. Yes. Now we're gonna move on to the power of power rule. Pretty much you're raising some power to an exponent. It's just as if you're multiplying the exponents. So look, once again, the idea, the expectation that you're familiar with this, but just to give like examples to renew the memory. You got 3 squared. You could solve it by first taking 3 squared, being okay, that's 9 squared, and then that's 81. Or you could take it as, 3 squared, that's 3, 2 times 2, 4, which is also 81. Same thing. So for this one, we're going to take a slightly different route. Okay, so let's just recall our definition. Where log base a of a to the x equals x. And similarly, log base a of a to the square equals square. Whatever is here when our base is a. So let's first look at this side, right hand side. Log base a of x, log base a to 2x times y base a equals x times y. And then left hand side, so this lovely young exponent, young power I should say, log base a of a to the x y equals right hand side, which is x times y. Okay, cool. We're gonna write that all together, or I was gonna summarize this here just to make it easier to move on. So a raised to x times y is equal to a to the x power of y. Okay. What is this x? X is the power exponent when a is raised to it. Well, will give us b, but whatever. X is this. The value that when a is raised to it gives you a to the x. Cool. Let's write that. Log base a. It's just another rephrasing, but a helpful rephrasing. I'll change the order so I don't have to clarify things here. A to the x. Generally, you won't actually know what this a to the x is. It could be any value because, like, it probably won't be given to you on a silver platter because then you just can solve the problem easily. I'm gonna assume you're probably gonna see problems that are more like log base 2 of 7 instead of log, oh, it's a horrible example. Log base 2 of 8 as opposed to log base 2 of 2 cubed. So we're gonna keep it in this form when solving or when trying to find some helpful log manipulation. So let a to the x equal b. Okay, so the value that when a raised to it gives us b to the power of y is also equal to y times log base a of b. Oh, cool. So we see that this falls outside. Now that we've done like the steps, we see that it makes sense in that like it's all flowing from how a power raised to some exponent is same as just multiplying the exponents to begin with. Here, we're raising a power, a to the x, which is b, raising that to y. But by raising that to y, we're just multiplying the exponent x with the exponent y, right? In this case, this is the exponent x, and that's the exponent y. I have highlighters for a reason. Okay. The exponent x, multiplying it by the exponent y, in both cases. So that's why these are equivalent. And it makes sense why this is our final answer and final line. It's just sometimes easy to overlook that b is just the value of a raised up to some number. That's why perhaps when given this form it can be kind of weird. At least personally it was when I first learned this. Okay. Let's make it all nice and bright. Oh, let me know if I should post this as well. Because, I mean, if I do post it, I'll make it look prettier. Okay, so just let me know if you're interested and if it'd be helpful. Okay. Last but not least, we got this third. This is less of an exponent law that I'm manipulating, but more of a manipulating the ability to express things in many ways. From this, we're going to derive the log law of change, or the change of base formula. Perhaps less of a log law. Change of base formula. Nice. Okay. So first, we're going to do like a few steps. Use what we found before, get a final solution, and then we're going to understand what that final solution is really trying to do. And the steps will become more clear after that. A lot of time it does end up being that way. You try something, you're like, okay, cool, weird, I'll keep trying different things, and I'll keep going through this attempt, and then you'll get something. So we're going to do that here. You explore by not understanding what you're doing at first. Sometimes. Okay. So, what we're going to do is we're going to take a to the x equal to b. Right? Our friendly neighborhood equation or expression. Equation. Take log base c at both sides. So we're trying to see what must c be raised to get to both of these. We're going to work out our x, which we found in the previous log law. Log base c of b. In 0, we see your x, just divide both sides by log base c of a. We got log base c of b, divide by log base c of a. That's x. And don't forget, we're going to keep going back to this because it's important. X is just log base a of b. So we can erase this. And look at that. It's a change of base formula. Beautiful. So what is this ratio really trying to say? We can look into this by considering it from the power exponent side. So we said let a to the x equal b. Cool. Now let c to the power of y equal a. So if we wanted to express b in terms of c, say like we knew what the values, we had a better handle on log base c than log base a, so we wanted to find b in terms of c. We would do this. Let's see. Okay, in terms of c, it would be c to the y, the power of x, equals b. So c to the power of y is a, and then that's the power of x. So we got c to the y x equal to b. once again, we got our a in terms of c. So if we look at our exponents, they're telling us how much c do I need to get b? How much c do I need to get a? So y over x over y is just saying number of c's for a b, number of c's for an a, which gives us, actually, this guy right here. I have to erase the thing. That is fine. Okay, paste. Once again, because we're just extracting here, yx. Oh, let's pick a nice color. Yx is that, because it's this exponent, and y, not from here, just that. Because once again, we are extracting the exponent that c must be raised to. Apparently, that gives us log base a of b, or number of a's for a b. If you wanna, that may be like too many words, so let's just look at a little example here just to clarify things. Let's say that c times c equals a, and c times c times c times c times c times c equals b. So let's get that down here. Number of c's for a b, well, there are 6 of them, and number of c's for an a, there are 2 of them. So what we're just doing is grouping together the number of a's that are in b, right? We're saying, okay, this is an a, let's now divide the 6 by 2. And so how many of these 2 c's do we have? Oh, there are 1, 2, 3 of them. So this equals, in this particular case, 3. Okay. That's pretty much what we're doing. We're just expressing it, expressing A and B, using C, something different. And seeing how much C's make it a B, how many C's make an A, and then using that ratio to find how many A's are in B. So that's why this is equivalent. A little bit of a roundabout way to get to it. Let me know if there are better ways to write it. Perhaps a nicer way. Okay, I'm just going to erase the example. A log base c of c to the yx, which once again, that's what b is. and divided by log base c of c to y, just yx over y. Which one divided out, right, will give us our x. One second. Yay. Oh, I'm so tired. Beautiful. And till next time. Bye.